Dear student, today again I am going to discuss about the numerical problem based on the capacitor. And yesterday in the previous video already I have discussed up to the case number 2 regarding the numerical problem based on the capacitor. Today I am going to discuss about the case number 3. If any circuit of the capacitor is given like this one, in which C1, C2, C3, C4 be arranged according to, along the arms of a parallelogram, then you can say this one is called a Wheatstone bridge arrangement. And in this Wheatstone bridge arrangement, if the ratio of C1 and C2, if C1 upon C2 is equal to C3 upon C4. So first, if any arrangement is given like this, then first you will check the ratio of these two capacitor and the ratio of these two capacitor. If their ratio are equal, then you can say this bridge is said to be in balance condition. And in balance condition of this Wheatstone bridge, the potential at point C and the potential at point D becomes equal. But this potential will be equal under what condition? When the bridge is in balance. And how can you check the balance condition? By taking their ratio. So first you will take the ratio of C1, C2 and then C3, C4. If the ratio are equal, then you can say this bridge is in balance, and then the potential at point C and D are equal. And if the potential at point C and D are equal, then the potential difference across this capacitor is 0. Here potential is equal. So potential difference across this capacitor C5 is 0. And you know Q is equal to CV. If V is the potential difference across the capacitor is 0, then you can say this charge on this capacitor will be also 0. And a capacitor without charge in any circuit be useless, and that capacitor will never counted in equivalent capacitance. So dear student, in this case, this C5 capacitor, simply you can remove it because it is useless and no any charge is stored by it. So in this diagram also you can remove it. Now you see here, your aim is to find the equivalent capacitance between A and B. So for this case you see here, these two capacitors are in series. So first you will find out the equivalent capacitance of C1, C2, but remember the C1, C2 are in series. First you will find out their equivalent. Again C3 and C4 are in series. Again you will find their equivalent, and now this equivalent and this equivalent both are in parallel across AB. And by taking their equivalent and this equivalent, again you will suppose the equivalent of C1 and C2, and this C1 C2 equivalent is suppose C dash. So you can say this C dash is equal to C1 C2 upon C1 plus C2. This is the formula for finding the equivalent capacitance when two capacitors are joined in series. Suppose this C dash is the equivalent of C1 C2. Similarly, C double dash is the equivalent of C3 and C4. So you can write C double dash is equal to C3 into C4 upon C3 plus C4. And you will calculate this one, C dash and C double dash. Now at place of these two capacitor, we can put a single capacitor C dash, and at the place of these two capacitor, we can put a single capacitor C double dash. And now it comes like this one. This one is C dash and this one is C double dash between A and B. And now the equivalent capacitance you calculate C equivalent is equal to C dash plus C double dash because both are in parallel. Suppose this capacitor is given. Now at place of C1, C2, C3, C4, I am taking the numerical value. Suppose this 2 microfarad, this one is 2 microfarad, this one is 3 microfarad, 3 microfarad, and this one is 5 microfarad. And our aim is to find the equivalent capacitance between A and B. So first you will check in this Wheatstone bridge arrangement, this bridge is balanced or not. And how can you check this bridge is balanced or not? So first you will take the ratio of these two capacitor, and ratio of these two capacitor is 2 by 2, which is 1. And again you will take the ratio of these two capacitor, and the ratio of these two capacitor is 3 by 3 is equal to 1, and the ratio are equal. It means this bridge is said to be in balanced condition, and in the balanced condition the potential at point C and D are equal. So the potential difference across CD is 0, and no any charge is stored in this capacitor of 5 microfarad. And a capacitor without charge in any circuit be always useless. So simply you can remove this 5 microfarad. It means 5 microfarad capacitor is useless for this. You can remove it from the circuit. It means in the next circuit when you will draw, then you can remove it. Now you see here, this 2 microfarad and 2 microfarad, these are 1 by 1 alternately connected. So these 2 microfarad are in series. Again this 3 microfarad are in series. So their equivalent, suppose their equivalent is C dash. So we can write C dash is equal to 2 into 2 upon 2 plus 2. If two capacitors are joined in series, then their formula you know, C1 C2 upon C1 plus C2. This becomes 4 upon 4 is equal to 1. Unit be always microfarad. Similarly, the equivalent of this 3 microfarad and this 3 microfarad. Suppose this one is C double dash. So 3 into 3 upon 3 plus 3. And now this one is 9 by 6. 9 by 6 means 1.5 microfarad. And now you can say at place of 2 and 2 microfarad, we can put a single capacitor of 1 microfarad. And again at place of this 3 and 3 microfarad, we can put a single capacitor of 1.5 microfarad. This point is A, this point is B, and now their equivalent, C equivalent, you can calculate C dash plus C double dash, because both are in parallel across AB. So you can write this is equal to 1 plus 1.5 is equal to 2.5 microfarad. So in this way you can find the equivalent capacitance if any capacitor is given in the bridge arrangement form. If any arrangement is given like this, so this arrangement can also be arranged in the form of Wheatstone bridge. How? Suppose in this arrangement your aim is to find the equivalent capacitance between P and Q. And in this case, for finding the equivalent capacitance between P and Q, so first you will look here, P, Q, this one is R, this one is S. So try to arrange whole this arrangement in the form of Wheatstone bridge form. How? Suppose this one is P, this one is Q, and this one is R, and this one is S. This one. So first you see here, across P to R, P to R, one capacitor C1 is connected. So suppose this point P to R, this capacitor C1 is connected. Suppose this one is C1. Similarly, you see here, R to Q, C2 is connected. Like this, P to R, C1 is connected. R to Q, C2 is connected. So this point is, look here, R, this one is Q. So R to Q, this capacitor C2 is connected. Again you see here, P to S, C3 is connected. P to S, C3 is connected. And S to Q, C4 is connected. S to Q, C4 is connected here. And again S to R, C5 is connected. It means S to R, this one is what here, C5 is connected.